Hello, today we will have our first lecture about electromagnetism. This lecture will be basically about electricity. The next lecture will be about magnetism, and the second and the last lecture, the third one, will be about connecting these things about electromagnetism, because these phenomena are closely related. As you know, gravity, Newton's gravitational force, of gravitation is constant K times, let's call it big mass, large mass, small mass, divided by r squared. Maybe we can write it like in more, in like this manner. This is not very usual writing, but it's mathematically the same. So gravitational force holds masses in place because masses are huge of planets, and planet of the Earth is huge compared to our mass. So this force is quite large, not quite, but large. But atoms, atomic particles, have small masses. So gravitational force would be very weak, and it would not hold all atomic particles in their respective places, locations. So it would not be possible for atoms to exist. So atomic particles are held in place. I'm basically talking about protons and electrons because they are attracted to each other. So protons, which have plus charge, and electrons, which have negative charge, they are attracted to each other. They are attracted by electric force. Also, there is this force is in general called electromagnetic, because also there is magnetic interaction, magnetic forces. So basically, when we say that atoms are protons and electrons are in the atom are held the same by electromagnetic forces, and atoms in matter, what's important for us, are held by so protons and electrons and atoms in matter are held by electromagnetic forces. So as you know, electromagnetic forces, let's say about begin with electric charge. So electric charge is positive and negative. This is we just mark this gravitational force. We will make comparison with electric force. So positive and negative charges, similar charges, they repel each other. If we have two, so you know, two pluses, so this plus pushes this plus there, this plus pushes this plus there. So if one is in red, so it pushes the blue one, and the blue one pushes the red one. If they are different charges, this is plus, this is minus, so minus attracts this one, minus attracts plus, plus attracts minus. Usually matter has equal number of positive and negative electric charges. So it is neutral. Atom has the same number of protons and electrons, so it is also neutral. So we can write that number, this stands for number of electrons is equal to number of protons. That's how I would write. Yes, number of electrons is equal to number of protons. As you know, basically, atom, if we are speaking here about atom, has nucleus. So nucleus is composed of protons and neutrons. So protons have plus charge, positive charge. It's probably you probably can't see. So protons have plus charge. Neutrons they don't have charge, and electron is spinning around the nucleus in an orbit. It's like orbital motion, but later we will see that electron can be understood as a wave, so it would be like electron cloud. But anyway, nucleus is composed of protons and neutrons. Protons plus charge, neutron has no charge. Around nucleus, electrons orbit. They are electrons move in a line that it's like orbital motion, like in orbits. Okay. In orbits. Okay, so electron 1, another electron would be moving here. So we will speak about structure of atoms later. So nucleus, protons and neutrons, and around nucleus there are electrons. Now the charge is usually denoted in capital Q letter or small q letter. So charge of electron is minus 1.6 times 10 to the minus 19 Coulomb. Coulomb is the unit of electric charge, and proton is positive charge, the same charge, very small charge. 10 to the minus 19 coulomb. So compared to 1 coulomb is large charge. So if we compare, we will see this later. So now this is gravitational force. So we can see now that I will rewrite this equation because we don't have place in that paper. F gravitation, so would be K capital M small m and R squared. It's distance between masses. So now the force, Coulomb force, so Coulomb force is the electric force, is for the name of Coulomb, the scientist who scientifically defined this force. It is K capital Q small q divided by R squared. So you know, if you know mechanics, so then it means that this mechanics and mechanical gravitational force and Coulomb force, they are, you see, written in the same place, except for mass there is charge. And so if you were studying mechanics pretty well, you will understand electricity. So this is called Coulomb force, the electric force between two charges. So plus and plus. So there is distance between them R, and they are pushed by F Coulomb so if this was red, it pushes the blue one, and this blue one pushes the red one. So they are pushing. If there is, as we shown, if the signs are different, then there is attraction force between these two. So Coulomb force here between two charges. Let's write this one capital Q. Can write this one as small q, or we can write that in two capital Q's, or it doesn't really matter. But this force, Coulomb's force, the same like gravitational force. If you have a planet, let's say if you have sun, or if you have just, let's say you have Earth. If you have Earth and there is moon, let's say there is moon, so moon is attracted to Earth, Earth is attracted to moon, so the forces are the same. They should be the same. Do they look the same? Let's say they are the same. These should be the same length. How is in physics there is a concept of field, force field, that this field, this force, gravitational force, is transmitted through space in a field. So imagine that there is a field around Earth, gravitational field, that if an object having mass is positioned in this field, so it goes to the center of the Earth. So this force to the center of the earth. So if you position a mass in this force field, it would be a vector field. We can draw more lines, it doesn't really matter. So if you position a mass somewhere here, it will go here according to this arrow. This arrow shows here. So if you position a mass here, this mass goes here. If you position a mass here, this goes to the center of the earth. If you position mass here, this will go to the center of the earth, as this arrow shows. Here it is this arrow. Position mass here, goes here. If this arrow shows to this, position mass here, it will go here. So the mass goes to the center of the earth, and gravitational force is transmitted through space via gravitational field. So the same is with electric charge. If we have electric charge, so Coulomb's force, K capital Q small q divided by R. So if we have this big charge, large charge, and we have small charge, small plus, maybe too small, so small plus, so this small q, so this q is, make this red, is pushed. Maybe I will redraw this. Let's make it big charge, plus Q, and make it this small, plus. So this would be big charge, and it pushes the small charge here. This small charge, because it is held very small, so very small, so it means that this is so small that it cannot, it pushes this charge, of course it pushes, but it makes so much it pushes by the same force. As it here, but this the magnitude of this charge is held so small compared to this one. So this Coulomb force is written like this, like we had written before. So so it means that this big charge is large charge is having is pushing this small charge to the right in this case, and as we were speaking about gravitational field, this produces electric field. So electric field is shown having the lines, the directions that would push small electric charge. So if it is large charge, so it would push this charge to this direction. If this charge was placed here, so it would push this small charge to the right. Doesn't matter, it can be put here, put here. This small charge doesn't matter. If we put this charge here, so it will be pushed here. If we put this charge here, it would be pushed here. If we put it here, it would be pushed here, pushed here. Now here to this direction if put here, and to this direction if it was put somewhere here or here. So you see what the pattern that electric field of this red charge has on small positive charge put there. It is a definition that we are analyzing small positive charge. Where would that small positive charge would go? So this is by definition that we are analyzing small positive charge, that it is positive, not negative. So it's going here. So now electric field, the strength of electric field, it is defined by F Coulomb divided by this small q, and this would be K capital Q small q R squared. I forgot to write R squared. Let's write R squared everywhere. Here we can write R squared, but this didn't matter. So here I wrote R squared, and here I wrote R squared. So now I was correct there. Now I'm correct again. So now we divide by this Q, and we write that it is KQ R squared. So E is what? E is K times capital Q R squared. So it means that the electric field strength of this charge, this big charge, does not depend on this small charge. So you can does not depend on the small charge. So it's the characteristics only of this. So electric field is characteristics only of this large charge. So you can put it 2 coulombs, 3 coulombs, 5 coulombs, and you just multiply electric charge, this electric field strength by small q, and you will get coulombs force according to this equation. Yes, so you just multiply by this cross. So F coulomb, it would be this big electric field strength of this large charge times small q, which is positioned. It can be 1 coulomb, 2 coulombs anyway. So this is characteristics for only this big large charge. So units for this is force divided by charge, so it would be newtons for coulomb. Also it's measured in volts per meter, but to derive this we would need more advanced studies on this. So newtons for coulomb, how much force experiences the charge positioned in this electric field. So we position this small plus charge, and it experiences some force, some newtons. It experiences some newtons. So newtons per unit charge, newtons for 1 coulomb. What's next? So if you see, if we thought about electric fields, so electric field lines of different charges are different. You see, if we have plus charge, so then the small positive charge would move as we have shown. It would move to these directions, so small positive charge If we have negative charge, so it would move to, the arrows would change, direction of arrows. So it would move to the negative charge. So if we put small plus, it would move to, is attracted. If we have the configuration of positive and negative charges, so then the small positive charge would move from positive to negative charge. If we put it here, it would move, it would go down, as it shows here, down, but it's attracted by this, so it would curl like this. If it was put here, it would go here and curve by this, so it would make turn like this. And other configurations are like this. So these are the directions of small positive charge. So you see how it would go like this. We put it here, it is pushed down by this one, pushed down by this one, and it would be then attracted by this one, by minus. So small plus is pushed down, then straight down, and then is attracted by this one, so it goes down, but then it is curved here. The strongest electric field is closest to the charge, is the closest to the charge. So the density of these lines, so here the lines are the densiest here, has the highest density around this. So here we have, if we draw more lines, then we can see probably that denser the lines are close to this center of the charge, so there the field is the strongest. And if we have two parallel plates, so this has positive charge, this has negative charge, so electric field is shown like this, and it means that it is homogeneous electric field. It has the same magnitude everywhere. So you see that the density of the lines is everywhere the same. It's shown from plus to minus. Small positive charge would move in a straight line from plus to minus, positioned everywhere. So now materials. Speaking about materials, materials according to their electrical properties are classified to conductors and non-conductors. So these are insulators. So this is based on how well they allow electric current to pass. So conductors generally have low resistance. These have high resistance to current. These have low resistance. These are usually metals and salt water also. It is a good conductor, but not pure water. Non-conductors would be glass, plastic, ceramics, dry air, pure water. So copper wires have plastic sheath, so that for protection, for insulation. So these conductors and non-conductors, they all have, they are neutral, so it means they have the same number of positive and negative charge. So number of minuses is equal to number of pluses. So they both are neutral, but in conductors there are, there are atoms. So if we have atom, let's say atom is neutral, but there are electrons, and these electrons, nucleus has plus charge, electron has minus charge, so these electrons are free to move everywhere. So this electron can move to this atom, this electron can move to this atom, this can go to this can go to this, so they can switch places. So that's why these electrons are not bound to particular atom, and these electrons are called homeless electrons. And here electrons are bound to particular atom in non-conductors. So electrons are free to move. Here electrons are not free to move. For this case, if conductor is positioned in external electric field, let's say, maybe let's take another sheet. So conductor in external electric field. So if conductor is positioned in external electric field, so between two parallel plates, so imagine that we would place a conductor here. So what happens? So in this external, so electrons from this side, this part, would move to this part. So they would all move to this part because they are attracted. So this would have negative charge. So leaving the unbalanced pluses here. So the lines of electric field go from plus to minus. So this means that here there is, in the conductor, there is electric field. So red cancels blue field, so red field cancels blue field, and the conclusion is that there is no electric field inside the conductor. So two vectors, blue vector and red vector. So the sum of these two is 0. Now what else? So this is used for electrostatic shielding. So if you have some kind of object, let's say if a human is inside a metal object, let this would be metal object. So, and let's say that this human is in external electric field. So this, let's say this is metal object. So this metal circular, in this case object, would act the same. Minuses would go here, pluses would be here. Forgot to draw this. Plus to minus, so they would create field opposite to this blue one, and these two fields would cancel out, and the net electric field inside the conductor would be 0. So human would not be affected by this electric field. So for this reason, if you are in the car, you are not hit by lightning, but about electric current we will see later. But if there's electric field is necessary for charge to flow, so current flows if there's electric field. If there's no electric field, the current can flow, so lightning can't hit you, and the human is safe here. So this is electrostatic shielding. It's called also the Faraday's cage. Now, insulators. Insulators in external electric field. So insulators also are neutral, but they have molecules that have plus and minus sides. So this molecule has the same pluses, the same minus, so has plus charge and minus charge, but in different sides. So it means there are poles, electric poles. So if this kind of molecule is positioned in external electric field between two parallel plates, so in a material, because because this plus because it has electric poles, so what happens? So if it has electric poles, it can create electric field like this, you see, plus and minus here. So if it has these poles, so it means that it creates electric field. So small plus, small minus, and it can create electric field by itself. So as we were drawing, so it creates electric field the same as we were drawing. So it creates electric field, but because in the substance they are randomly in the material they are randomly distributed in a sample of material, so these electric fields, they cancel each other out. But if this molecule is positioned in external electric field, so this plus is attracted to this side, maybe I will draw in blue. This plus is attracted to this side, this minus is attracted to this side. So this molecule experiences a torque. So it means that this rotational motion around this axis, it turns. So, and what happens? And happens that thing that if you have parallel plates and you have plus, from plus going to minus electric field lines, external electric field, you can write this. So molecules that are positioned, so we'll have minus side here, plus side here, minus side here, plus side here, minus side here, plus here, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus, and minus, plus. So they would produce, so they are aligned in this case and not randomly distributed as if there were no external electric field. So they produce electric field from plus to minus of their own. But this electric field is small compared to the external electric field, so it is not completely zero, not completely cancelled out, but it's only diminished. So external electric field is diminished in an insulator. So only diminished. So it is usually written by this epsilon, this letter. I probably you don't need these equations, too many equations for you. So just remember that in an insulator it is diminished, and external electric field is cancelled out in conductor. In conductor it is cancelled out. Remember, 1, 2. Okay, now what else is happening? What else is happening? So there is electric field and electric potential. Electric potential. If you have two parallel plates, what's happening? You put electron in here. What's happening with the electron? It moves. Where does it move? It's pushed to the right from the plus and attracted to the minus, so it moves here. Sorry, if you put positive charge here, what happens? If you put positive charge, it moves from left to the right. Positive charge here, it moves there, it moves here, as the lines show. Now if you put electron, of course, because lines are agreed to be from positive to negative of the external field, so if you put electron here, it has negative charge, it would move here in reverse direction to the lines. This is how it is defined and how it behaves. These the direction of lines only that are in agreement historically. So electron moves from minus to plus, so it means it moves in a reverse direction to the lines of the external electric field. Now, if you have a battery, so battery has two poles. It has plus pole and a minus pole. And it is a wire conducted to a battery. And imagine what's going on in the wire. You probably won't find this explanation anywhere, but what's going on in the wire? In the wire, this battery is a plus and minus. What is it, basically? It is nothing different than this thing. Imagine that it would be the same here. So you have a battery that has plus and minus terminals. So this is happening in the battery. Battery is producing external electric field. So remember that battery is producing external electric field. So if we see this small, so I wanted to draw here, so the same thing, this is plus. If we imagine what's happening in the wire, I just made this wire, imagine it was thicker if we went deeper into this wire. So this was external electric field, and electrons would be moving here to this direction. So it would be the same. Imagine if we thickened, if we went deeper into the wire to see what's happening in the wire. So it means that in the wire there are plus and minus. There is electric field in the wire produced by battery. So if there is electric field produced in this wire by battery, so it means it's produced here. It is produced here, it is produced here. So it means that this electron flow is happening in the wire. So wire produces electric field. Imagine this is we went deep into the wire, and we see that battery produces this electric field, blue one. Plus terminal is here, minus terminal is here, electric field goes here, and electrons of the wire that are in the wire, because the wire is what? It is a metal, and electrons are homeless electrons that can move. So battery produces external electric field, homeless, free electrons of wire move in that field. They try to cancel out batteries produced electric field. Why do they try to cancel out? Because wire is conductor in electric field created by battery. So as negative charges were moving from one side to another, trying to cancel out the external electric field, so the electrons of the wire, they try to cancel the electric field that battery creates in the wire, and by that they flow. So they flow. So this situation is happening at this point, at this point, at every point, at this point, at this, and eventually the electrons come to this terminal. They come to this terminal and they neutralize this plus. They neutralize this plus, but inside the battery there is a redistribution of charges. So when electron comes at this terminal, so this electron is reacting with this plus. So maybe that's right here. Electron comes to this terminal and it is equal to 0. But what happens? Chemical reaction here creates new electrons which go here. So it means that if this chemical reaction creates electrons which go here, also there has to be plus, which is this one, this plus. Let's make it here. Probably this plus goes here. So electrons eventually they combine with this plus to make 0, but chemical reaction inside the battery, it splits the atom. It splits the atom would be very sound was very profound saying, because splitting atom would be different thing in radioactivity, but imagine that it just splits electrons from atoms, and the electrons they move and makes electrons move here to the negative side, because if electrons leave this negative side becomes neutral. Imagine electrons are flowing, so this becomes neutral. So this, and they go from here and they enter here, so this becoming neutral, and because electrons coming to this plus, so this is becoming also neutral. So inside this battery, electrons are redistributed, charges are redistributed, so this is kept plus by battery and this is kept minus. So this is philosophical explanation what's happening here. It's, physical, philosophically. Basically, you will find in books only saying that electrons go from minus to plus, and that's it. So now what is electric potential? So electric potential is very difficult to understand, basically.